Welcome back to Civil Engineering Edge. Today, we're tackling a question every budding engineer and homeowner asks. Which building construction is best frame structure or load-bearing structure? We'll dive deep into each method, examine their strengths and weaknesses, and show you real-world examples to help you decide which suits your project. Let's get started. Section 1. Frame structure. Cut to animation of beams and columns. Frame structures rely on reinforced concrete or steel beams and columns to carry all building loads down to the foundation. The walls are non-load bearing, serving only as partitions or cladding. Key characteristics: load transfer. Beams transfer floor loads to columns, columns channel them to the foundation. Flexibility. Since walls aren't structural, you can easily modify or remove them for future renovations. Height and span. Ideal for high-rise buildings and large open-plan spaces, think skyscrapers and shopping malls. Construction speed. Prefabricated steel frames can speed up construction. Modular RC formwork systems also boost efficiency. Advantages: 1. Design freedom. Architects can create open lobbies, double-height atriums, or change room layouts without compromising structure. 2. Resistance to lateral loads. Well-designed frames perform strongly under wind and seismic forces thanks to ductile behavior of steel or reinforced concrete. 3. Service integration. Ducts, pipes, and wiring run through beams and columns easily, simplifying MEP coordination. Disadvantages: 1. Cost. Higher material and labor costs, especially for steel frames or high-performance concrete. 2. Thermal bridging. Steel frame junctions can conduct heat, requiring careful insulation detailing. 3. Fire protection. Exposed steel or RC elements need additional fireproofing coatings or thicker concrete covers. Best example: the Burj Khalifa, Dubai. Why it works. Standing at 828 meters, it's the tallest structure in the world thanks to its bundled tube RC frame system. Frame benefits in action. The RC core and perimeter columns resist wind forces, while podium floors span large areas for observation decks. Key takeaway: for ultra-tall buildings and expansive floor plates, frame structures are unparalleled in performance and adaptability. Section 2. Load-bearing structure. Cut to animation of brick walls supporting slabs directly. Load-bearing structures use walls made of brick, stone, or block masonry to carry roof and floor loads directly to the foundation. Beams and columns, if present, are secondary. Key characteristics: load transfer. Walls carry vertical loads and sometimes lateral loads, especially when reinforced. Simplicity. Construction relies on straightforward masonry techniques, familiar to most contractors. Cost effectiveness. In low-rise buildings with smaller spans, masonry walls are economical and readily available. Advantages: 1. Low initial cost. Masonry materials, clay bricks, concrete blocks are inexpensive and locally sourced in many regions. 2. Thermal mass. Thick walls provide good thermal insulation, keeping interiors cooler in summer and warmer in winter. 3. Fire resistance. Solid masonry walls naturally resist fire spread without extra coatings. Disadvantages: 1. Limited height and span. Practical for up to 2 to 3 stories. Walls thicker as buildings grow taller, reducing usable floor area. 2. Design constraints. Every partition may need to align with a load path, limiting open plan possibilities and design flexibility. 3. Seismic vulnerability. Unreinforced masonry performs poorly in earthquakes. Retrofitting is challenging. Best example: traditional rural homes in Kerala, India. Why it works. Single and double-story houses built with laterite blocks and lime mortar blend with local climate and materials. Load-bearing benefits in action. Thick walls provide excellent thermal comfort, while locally trained masons keep labor costs low. Key takeaway: for small, low-rise residential buildings in regions with minimal seismic risk, load-bearing construction remains a cost-effective, sustainable choice. Conclusion: both frame and load-bearing structures have clear pros and cons. Frame structures excel in height, flexibility, and resistance to dynamic loads, while load-bearing buildings shine in simplicity, cost, and thermal performance for low-rise designs. Your choice depends on project scale, budget, and local conditions. Transition shot: futuristic city skyline animation morphing into construction zones. As we step into the modern era where sustainability, resilience, and adaptability are paramount, choosing the right structural system is more critical than ever. Let's explore which construction method truly meets the demands of today and tomorrow. Section 3. Mod Adoption. To host walking through a BIM-enabled construction site. Modern construction isn't just about bricks or beams. It's about integrating technology, sustainability, and performance. So, which structure should you adopt for the best long-term value? 1. Sustainability and carbon footprint. Frame systems with low-carbon materials. Advances in high-performance concrete mixes, including supplementary cementitious materials like fly ash or slag, and engineered timbers. Cross-laminated timber (CLT) have slashed embodied carbon by up to 40%. A reinforced concrete or hybrid steel timber frame can be both strong and green. Life cycle optimization. Non-load-bearing walls allow for demountable partitions, extending a building's service life and reducing waste when spaces need repurposing. 2. Resilience and safety. Seismic and wind resistance. Modern frame structures equipped with base isolators, dampers, and tuned mass devices elegantly manage dynamic loads. Even tall timber hybrid frames can achieve high ductility and energy dissipation. Fire performance innovations. Intumescent coatings for steel frames and fire-resistant CLT layers mean modern frame buildings can meet the strictest fire codes without sacrificing open layouts. 3. Digital integration and prefabrication. BIM and modular construction. Frame systems lend themselves to off-site prefabrication, be it steel modules or volumetric timber pods, ensuring faster construction, higher quality control, and reduced on-site labor. Real-time clash detection in BIM models streamlines MEP integration. Smart building systems. Structural frames provide clear pathways for embedded sensors, wiring, and ducts. This simplifies implementation of IoT devices for structural health monitoring, energy management, and predictive maintenance. 4. Cost and speed. Economies of scale. As prefabrication technologies mature, unit costs drop. A steel timber hybrid frame can be erected at rates exceeding 1,000 square meters per week, dramatically cutting project schedules and financing costs. Adaptability over time. Frame buildings accommodate vertical expansions, adding floors easily by extending columns, maximizing land value in dense urban settings. Best example: Brock Commons Tallwood House, Vancouver. Why it works. This 18-story student residence uses a hybrid CLT and glulam timber frame wrapped in a concrete core. It boasts a 17% reduction in carbon footprint compared to an equivalent concrete-only tower. Modern era benefits. Prefabricated timber panels sped up construction by 30%, while integrated sensor networks monitor humidity and load in real time. In today's world, a modern frame structure, especially hybrid systems combining low-carbon concrete, steel, and engineered timber, delivers the optimal blend of sustainability, resilience, and flexibility. Whether you're planning a mid-rise office, a high-rise apartment, or a smart campus, embracing these innovations is the smartest choice for our evolving built environment. On-screen text: think modern, think hybrid frame. If you found this breakdown helpful, hit like, subscribe to Civil Engineering Edge, and let us know in the comments which method you choose for your next build. Stay tuned for more insights if you agree, and drop your questions below.